What if everything we know about the universe is just the surface of something far deeper, something hidden in plain sight? Picture gazing up at the night sky, where every star, every galaxy, seems to follow the rules we've mapped out over centuries. But what if those rules are just the beginning? Behind the curtain of the observable cosmos, there could be layers upon layers of reality we've barely begun to scratch. Dimensions folded like origami, forces whispering beyond the limits of our detectors, entire realms existing right alongside ours, unseen and untouched. This isn't science fiction, it's the cutting edge of what science dares to explore. For centuries, humanity has unraveled the universe's secrets, from gravity to black holes, yet each discovery only seems to reveal more questions. What's truly out there? Are we alone, or is the cosmos teeming with hidden structures, parallel universes, shadow matter, or even echoes of other dimensions brushing against our own? Some of the brightest minds alive are chasing these very ideas, proposing theories so bold they blur the line between physics and philosophy. And today, we're diving into 30 of the most astonishing among them. Theories that challenge not just what we know, but how we think about existence itself. This journey won't just stretch your imagination, it might redefine how you see reality. We'll explore whispers of a holographic universe where our three-dimensional world is merely a projection. We'll confront the eerie possibility that dark matter could be the tip of an iceberg, hiding entire civilizations we can't perceive. And we'll question whether time itself is an illusion, a flickering shadow of something far stranger. Buckle up, because by the end, the night sky will never look the same. The cosmos is stranger, wilder, and more mysterious than we've ever dared to dream. And the most thrilling part, we're just getting started. Imagine holding a photograph in your hands, a flat, two-dimensional image. Now picture stepping into that photo where flat shadows suddenly gain depth, texture, and movement. This isn't just a trick of the light, it might be the very nature of our universe. At the heart of our first theory lies a mind-bending proposition. What if our three-dimensional reality, with its towering mountains and swirling galaxies, is nothing more than a holographic projection? A cosmic illusion encoded on a distant, two-dimensional surface. The idea stems from an unexpected marriage of black hole physics and quantum mechanics. When scientists calculated the information needed to describe a black hole's event horizon, they found something startling. The maximum data it could hold didn't depend on its volume, but on its surface area. Like a pixelated screen, everything within the black hole could be represented on its boundary. This led physicists like Leonard Susskind to ask, could the entire universe work the same way? That the stars, planets, even your own thoughts, might be intricate projections from a flat, distant surface we can't see. Quantum entanglement adds another layer of strangeness. Particles separated by vast distances can mirror each other's states instantly, as if space between them doesn't exist. This spooky action at a distance, as Einstein called it, might be a clue, a hint that deeper, hidden connections stitch reality together from some fundamental layer. Experiments like Fermilab's holometer have hunted for evidence, searching for minuscule pixel-like vibrations in spacetime itself. While results remain inconclusive, the implications are staggering. If true, the universe isn't just described by information, it is information, a shimmering hologram where depth is an elegant trick. Think of it like watching a 3D movie without glasses. The illusion collapses into blurry layers. If the holographic principle holds, our entire existence might be a cosmic rendering, with the real action happening on a shadowy, two-dimensional stage at the edge of everything. It's a theory that doesn't just rearrange the universe, it dissolves the line between the physical and the abstract, leaving us questioning whether reality is as solid as it feels. Now, let's shatter the idea of a single, linear universe and step into a reality where every choice you make, every breath, every hesitation spawns an entirely new world. This is the many worlds interpretation, a quantum theory so radical it suggests our universe is just one thread in an infinite, ever-expanding tapestry of parallel realities. Forget Schrödinger's famous cat trapped in a box both dead and alive here. The cat doesn't just exist in two states. It's alive in one universe, prancing around happily, while in another it meets its fate. And in countless others, perhaps it never even entered the box at all. The roots of this idea stretch back to the bizarre behavior of quantum particles. When scientists observe these tiny building blocks of reality, they seem to behave differently than when unobserved, as if reality itself splits based on measurement. Hugh Everett, the physicist who proposed this theory in the 1950s, dared to ask, what if every possible outcome does happen but in separate, branching universes? Your decision to turn left instead of right at a crossroads doesn't just alter your path, it fractures time, creating a new reality where the other version of you drives straight ahead. Think of it like a cosmic choose-your-own-adventure book, except every possible ending unfolds simultaneously. Lost your keys this morning, somewhere out there, a version of you found them effortlessly. Missed a life-changing opportunity, in another reality you seized it, and who knows how differently that world turned out. The implications are dizzying. Wars might have ended differently, extinct species could still thrive, and historical figures might have lived entirely alternate lives. Critics argue this theory is untestable, a philosophical thought experiment rather than hard science. But supporters point to quantum computing, where particles seem to perform calculations across multiple states at once, as if borrowing processing power from unseen realities. Whether the multiverse is science's next great frontier or a fascinating dead end, one thing's certain: it forces us to confront the unnerving possibility that we're not just passive observers of reality, but active participants, spinning off new worlds with every flicker of thought. What if the mysterious substance we call dark matter isn't just invisible, but literally out of reach, tucked away in dimensions beyond our own? For decades, scientists have known something strange is happening in the cosmos. Galaxies spin too fast to hold themselves together with just visible matter. Cosmic structures bend light in ways that defy gravity's normal rules, and yet we've never directly detected what's causing it. Dark matter makes up over 80% of the universe's mass, but it's utterly silent, passing through you right now like a ghost. The unsettling truth: we might be searching in the wrong dimension entirely. String theory, the ambitious framework aiming to unify all forces of nature, suggests reality might have 11 dimensions, not just the 3 of space and 1 of time we experience. These extra dimensions could be curled up incredibly tiny, like a soda straw viewed from a distance, seemingly one-dimensional until you zoom in to see its hidden circumference. But here's the twist: some theories propose dark matter particles aren't just hiding in plain sight, they're leaking into our world from these folded dimensions. They're gravity-felt, but their forms forever out of view. Imagine living on the surface of a pond, unaware of the world beneath the water. Fish darting below might create ripples you can see, even if you never glimpse the fish themselves. Dark matter could be like those hidden creatures, its gravitational ripples warping galaxies while the particles themselves reside in dimensions we can't access. The Large Hadron Collider has hunted for signs of these extra dimensions by smashing protons together at nearly light speed, hoping to catch a fleeting glimpse of energy disappearing into unseen realms. While no definitive proof has emerged, the math is tantalizing. Certain vibrations of theoretical strings in these higher dimensions would perfectly match the properties we expect from dark matter. This idea turns our cosmic loneliness upside down. If dark matter is anchored in other dimensions, entire civilizations could thrive there, built from particles that don't interact with ours except through gravity. Stars might burn, planets might orbit, all invisible, all just out of phase with our reality. It's a humbling thought. the universe we see may be just one slice of an unimaginably vast multidimensional loaf where dark matter is simply the crumbs brushing against our familiar world. And if we ever prove it, the boundaries of reality would stretch far beyond anything we've ever dared to imagine. What if our entire universe, every star, every atom, every fleeting thought, is nothing more than lines of code in an unfathomably advanced simulation? This isn't the plot of a sci-fi movie. It's the simulation hypothesis, a theory gaining startling traction among scientists and tech visionaries alike. Elon Musk famously put the odds at 1,000,000,000 to 1 that we're living in base reality, and philosopher Nick Bostrom laid out a chilling trilemma. At least one of these statements must be true. Either civilizations always go extinct before reaching simulation capability, they choose not to simulate reality, or we're almost certainly living in someone else's digital construct. Think of it like this: if even one civilization in the universe's history developed the power to create hyper-realistic simulations, say, ancestor programs to study their past, the number of simulated beings would quickly dwarf those in the original, real world. Statistically, the odds tilt heavily toward us being among the simulations. The idea gains eerie plausibility when you consider the pixelated nature of reality itself. At the quantum level, particles behave like pixels, snapping between states without intermediate steps, almost as if the universe is rendering its details on demand. Even the speed of light could be a built-in limit, preventing the simulation from overloading. But how would we ever know? Some propose looking for glitches, unexplained mathematical constants, or cosmic anomalies that resemble programming shortcuts. Others suggest we might never break the simulation's illusion, just as characters in a video game can't perceive the computer running them, the most unsettling implication. If we're simulations, our creators might be too, nested like digital Russian dolls in an infinite regression of simulated realities. Yet the hypothesis isn't without pushback. Critics argue it's unfalsifiable, a modern reimagining of philosophical solipsism. But whether you find it terrifying or liberating, the simulation hypothesis forces a profound question. If reality is code, does that make the universe less real, or the act of creation more extraordinary? After all, in a simulation where every quark and supernova is accounted for, the line between artificial and real might vanish entirely. Picture waking up in total darkness, no body, no memories, just raw consciousness flickering into existence for a single moment before dissolving back into the void. According to the Boltzmann Brain paradox, this horrifying scenario isn't just possible, it might be more likely than the stable reality we take for granted. The theory hinges on one of physics' most unsettling ideas. Given enough time, randomness can create order, even something as complex as a fully formed, self-aware mind. And if that's true, how can we ever trust that our memories, the world around us, even the laws of physics themselves, are real? The paradox stems from Ludwig Boltzmann's work on entropy, the inevitable drift of the universe toward disorder. But here's the twist: in a cosmos that lasts forever, even the rarest fluctuations become inevitable. Atoms crashing together by pure chance could statistically arrange themselves into a functioning brain, complete with fabricated memories of a life that never happened. In fact, in an infinite universe, these phantom minds should outnumber real, biologically evolved beings by an unimaginable margin. So why don't we find ourselves as lonely Boltzmann brains, hallucinating reality for a split second before vanishing? Quantum mechanics adds fuel to the fire. In the vacuum of space, particles blink in and out of existence constantly, borrowing energy from nowhere in fleeting violations of physical laws. If space-time itself is frothing with these quantum fluctuations, could they, given enough eons, spontaneously assemble a conscious observer? Some cosmologists argue this very thought experiment undermines our confidence in the Big Bang's timeline, because if Boltzmann brains dominate the statistical forecast, why does our universe feel so stable and ordered? Critics counter that the paradox might be a red herring, a sign our theories of entropy or infinity need revising. Others propose a chilling escape. Perhaps the universe is teeming with Boltzmann brains, and we just happen to be among the rare, real observers. But the implications linger like a shadow. Every time you recall a childhood memory or trust the consistency of gravity, you're banking on cosmic probabilities that mathematically might not be in your favor. It's a theory that doesn't just question reality, it weaponizes uncertainty, leaving us to wonder if even doubt itself is an illusion conjured by a mind that shouldn't exist. Black holes devour everything in their path, unstoppable cosmic vacuums where even light can't escape. But what if their opposites exist? Enter white holes, hypothetical cosmic geysers where matter and energy erupt outward, forbidden from ever letting anything back in. While black holes trap, white holes explode. While black holes crush, white holes create. And if real, they might hold the key to one of cosmology's most radical ideas, that our universe didn't just begin with a big bang, but could be one in an endless cycle of cosmic death and rebirth. The math allows it. Einstein's equations describe black holes as tunnels through space-time, and if you follow those equations far enough, they suggest the other end could be a white hole, a furious fountain of particles blasting into a new reality. Picture a river plunging into a whirlpool, the black hole, only to emerge elsewhere as a roaring waterfall, the white hole. Some theorists, like Carlo Rovelli, propose that when a black hole dies, evaporating via Hawking radiation over eons, it doesn't vanish. Instead, it reboots as a white hole, spewing out transformed matter like a phoenix rising from quantum ash. Now scale this up. If tiny black holes can rebirth as white holes, could the same apply to our entire universe? The Big Bounce theory imagines a cosmos where expansion eventually reverses, collapsing everything back into a singularity, only for that singularity to erupt anew as a white hole, birthing the next universe in an infinite loop. Ancient Hindu texts described a cyclical cosmos of creation and destruction spanning trillions of years. Modern physics might be stumbling toward a similar conclusion, with white holes as the cosmic reset button. Evidence remains elusive, but clues tantalize. Some argue gamma-ray bursts, the most violent explosions in the universe, could be white holes flickering to life. Others suggest the Big Bang itself bears the signature of a white hole event, a singularity not of collapse but of eruption. Skeptics counter that white holes violate thermodynamics, bleeding energy without a source. Yet quantum gravity hints that time itself might behave differently near these extremes, bending the rules we know. Whether white holes are mirages or cosmic cornerstones, their possibility reshapes our place in the universe. If black holes are endings, white holes might be beginnings, and if they're linked, our existence could be one chapter in an epic without end, where universes breathe in and out like lungs across eternity. We think of the universe as expanding, gentle, relentless, galaxies drifting apart like ships on an endless tide. But what if that expansion isn't just slow and steady? What if it's accelerating toward something far more violent? Enter phantom energy, a hypothetical form of dark energy so destructive it could tear the fabric of spacetime apart in a cataclysm cosmologists call the Big Rip. This isn't just some distant, theoretical threat. The evidence might already be hiding in the light of dying stars. Dark energy, that mysterious force driving the universe's accelerated expansion, makes up about 70% of the cosmos. For decades, we assumed its strength was constant, a gentle push on cosmic scales. But phantom energy flips that assumption on its head. Imagine pouring gasoline on a fire, except the fire is the universe itself, and the gasoline never runs out. If dark energy's density increases over time, its grip on spacetime would grow stronger, accelerating expansion to terrifying extremes. First, galaxies would vanish over the cosmic horizon, their light stretched too thin to reach us. Then gravity itself would be overwhelmed, tearing apart Milky Way, then our solar system, then Earth, and finally, atoms themselves would be shredded as spacetime fractures at the seams. The clues lie in redshift. When astronomers measure light from distant supernova, they expect certain patterns in how that light stretches as the universe expands. But some observations show galaxies fleeing faster than predicted, as if something is pushing them apart harder than standard dark energy models allow. Phantom energy fits those anomalies perfectly, suggesting expansion isn't just steady, it's escalating. The European Space Agency's Euclid telescope is hunting for more evidence right now, mapping billions of galaxies to see if their movements betray this accelerating doom. But here's the twist: phantom energy might not just destroy, it could erase. In a big rip scenario, the universe doesn't just end with heat or cold, but with spacetime itself losing meaning. Distances become infinite in an instant, causality breaks down, and the universe ceases to cohere. It's not death, but dissolution. Some theorists argue this could even prevent new universes from forming, making the Big Rip the true, irreversible end of everything. Others speculate that phantom energy's violence might birth something stranger, a quantum foam where new spacetime bubbles emerge from the wreckage. Whether it's the universe's final scream or a transformation we can't yet comprehend, the phantom energy hypothesis forces us to confront a chilling truth: the cosmos might not fade quietly into the night. It could go out with a roar, unraveling reality itself in a finale beyond all human scales of time and imagination. And if the redshift data is right, this apocalypse might already be in motion, ticking away in the dark between the stars. Forget the Big Bang. What if our universe began with a collision? The ekpyrotic universe theory dares to rewrite cosmic origins entirely, proposing that everything we know sprang from a violent, higher-dimensional crash. Picture two infinite sheets of reality, cosmic membranes, or brains for short, floating in a hidden dimension. These brains aren't static, they ripple, drift, and eventually slam together. The energy released in that cataclysmic moment could have ignited our universe, transforming a multidimensional fender bender into the fireball of creation itself. This idea emerges from string theory's most radical implications, that particles aren't dots but tiny, vibrating strings, and the fabric of reality could have far more than 3 spatial dimensions. In this framework, brains aren't just theoretical doodles, they're vast, dynamic planes where entire universes might reside, separated by dimensions we can't perceive. When two brains collide, their energy doesn't vanish. It concentrates, erupting into the matter, radiation, and space-time we recognize. The Big Bang wasn't a singular point then, but the echo of something far stranger, a clash of cosmic titans. Supporters point to the universe's startling uniformity. The cosmic microwave background, the afterglow of the early cosmos, shows near-perfect symmetry in all directions. Inflation theory explains this by proposing a fleeting period of hyper-expansion, smoothing wrinkles in spacetime. But the ekpyrotic model offers an alternative. The brain's collision was slow and perfectly aligned, like 2 panes of glass pressing together evenly, leaving no room for cosmic lumps. Even the mysterious dark energy tugging our universe apart might be a relic of these brains rebounding, still vibrating from their ancient encounter. Critics argue the theory is untestable. How do you observe dimensions beyond our own? Yet experiments like those searching for primordial gravitational waves could hold clues. If the universe began with a bang, those waves should ripple in a specific pattern. But if it started with a collision, the signal might differ. Some even speculate that cyclic brain collisions could spawn endless universes, each collision resetting the cosmic clock, making our universe just one page in an infinite flipbook of creation and destruction. The ekpyrotic universe doesn't just challenge our origin story, it redefines reality's architecture. If true, our cosmos isn't an island but a shadow, a blister on the surface of something vastly larger, where unseen dimensions hum with the echoes of collisions past and the tremors of collisions yet to come. Time crystals sound like something ripped from a physicist's fever dream. Structures that don't just exist in space but in time itself, ticking away with perpetual motion like a clock that never winds down. Nobel laureate Frank Wilczek first proposed these bizarre objects in 2012, defying one of science's most sacred laws, entropy's relentless march toward disorder. Imagine a snowflake that doesn't melt, but instead cycles through its intricate patterns forever, never losing energy, never slowing. That's the essence of a time crystal, a four-dimensional lattice where atoms don't just arrange themselves in space, but dance in perfect, unchanging rhythm through time. The audacity of this idea lies in its defiance of equilibrium. Most systems settle into stillness like a pendulum eventually hanging motionless, but time crystals can't. Their structure locks them into eternal oscillation, not because they're magically immune to entropy, but because their lowest energy state is dynamic, not static. Think of a car engine designed so that even at rest, its pistons keep moving not from burning fuel, but because the engine's very blueprint demands it. In 2017, experiments with chains of ytterbium ions confirmed this wasn't just theory. When nudged, the ions flipped predictably, their spins synchronizing in a rhythm resistant to decay. For the first time, scientists held proof of matter organized not just in space but in time. Now scale this up. If tiny lab-built crystals can exhibit this behavior, could the universe itself be a vast, nested time crystal? Some theorists speculate that spacetime's fundamental fabric might ripple with similar periodic structures, hidden in the quantum foam. Dark energy's mysterious push could even be a symptom of these cosmic-scale oscillations, like echoes of a grand, eternal beat. Even more radical is the idea that time itself might not flow smoothly, but tick in discrete steps, each moment a frame in the universe's infinite, unchanging film reel. Critics argue time crystals can't do anything. Their motion is locked, useless for perpetual motion machines. But supporters see deeper implications. If time crystals exist naturally, they might mark the first examples of a new phase of matter, one where the arrow of time isn't just a statistical fluke, but baked into reality's blueprint. From black holes to quantum fields, their existence could rewrite how we perceive order, chaos, and the very nature of change. After all, in a universe where even time can crystallize, the line between the impossible and the inevitable starts to blur. What if black holes aren't cosmic dead ends but gateways, and we're already on the other side? The black hole universe theory flips the script on creation, suggesting our entire cosmos might be the interior of a black hole born in some higher dimensional reality. This isn't just poetic symmetry, it's a radical solution to one of physics' biggest headaches, the black hole information paradox. When matter vanishes into a singularity, what happens to the information it carried? Hawking radiation hinted that black holes evaporate, seemingly erasing that data forever, a violation of quantum law. But if our universe is the result of that process, the paradox might solve itself. Think of a black hole's event horizon not as a one-way membrane, but as a transformational boundary. Just as a seed's shell cracks to birth a tree, the crushing singularity at a black hole's core could have rebounded, spewing out energy and matter in a fireball we now call the Big Bang. The math shockingly aligns. The estimated density of our early universe matches the predicted conditions inside a collapsing black hole. Even spacetime's expansion could be a relic of that initial explosion, like the stretching of a rubber sheet after a bullet passes through. Here's where it gets stranger. Black holes in our universe might themselves contain nested universes, each with their own laws of physics, a fractal matryoshka doll of realities. The information lost in a parent black hole wouldn't vanish. It would re-emerge, scrambled as the fundamental constants of the child universe. Your very existence could be a quantum translation of some long-vanished star's final scream. Skeptics argue this theory is untestable. How do you observe the outside of reality? Yet clues might hide in cosmic microwave background patterns or deviations from expected black hole behavior. If proven, the implications rewrite not just our origins, but our destiny. Are we the aftermath of some alien cosmos's collapse? And if so, does that make us the echo of a dead universe or the first breath of a new one? Space-time isn't the smooth, unbroken fabric we imagine. It's more like the froth on a cappuccino, seething with tiny bubbles that pop in and out of existence in flashes too brief to measure. At scales 100 billion times smaller than an atom, the vacuum of space churns with what physicists call quantum foam, a turbulent sea where the very concepts of here and now lose all meaning. Here, wormholes flicker like sparks in cosmic static, space-time twists into microscopic knots, and reality itself becomes a statistical dance of probabilities. This isn't poetic exaggeration, it's the prediction of quantum mechanics and general relativity crashing together at the edge of comprehension. John Wheeler, the physicist who coined the term black hole, first proposed this foamy texture of reality in the 1950s. His calculations suggested that at the Planck scale, a distance so tiny it makes atoms look like galaxies, gravity's rules break down. Instead of orderly curves, space-time becomes a probabilistic frenzy. Imagine blowing soap bubbles in a hurricane. Wormholes tunnel between points in an instant. Virtual particles borrow energy from nothingness, and the fabric of existence fluctuates so wildly that empty space becomes a misnomer. Wheeler's foam isn't just a curiosity. It might be the scaffolding underlying everything we perceive as solid and stable. The wildest implication, these fleeting wormholes could stitch the universe together in ways we're only beginning to grasp. Quantum entanglement, where particles instantly mirror each other across vast distances, might be explained by microscopic wormholes linking them through the foam. Even the force of gravity itself could emerge from this chaos, like the roar of a crowd arising from countless individual voices. Some models suggest that if we could freeze time and peer into the foam, we'd see space-time riddled with tunnels, some connecting distant stars, others bridging parallel universes, most collapsing before they're even born. Experiments remain elusive. Probing the Planck scale requires energies beyond our particle colliders. Yet indirect clues tantalize. When scientists measure the Casimir effect, where unseeable quantum fluctuations push metal plates together, they're glimpsing the foam's shadow. Even the quest for quantum gravity hints at this granularity, like pixels blurring into the smooth image of space-time we experience. The foam might be the universe's foundational code, too fine for us to read, but running beneath every galaxy, every atom, every thought. So the next time you stare at the night sky, remember, the vast, tranquil cosmos is an illusion of scale. Zoom in far enough and reality dissolves into a storm of potentialities. A reminder that the universe is far stranger, far more dynamic than our senses will ever let us see. Ever reached for a light switch in the dark, only for the room to seem to brighten before your fingers even touched it? That eerie sensation where perception and reality blur might hold the key to one of quantum physics' most profound mysteries. The von Neumann-Wigner interpretation takes the baffling observer effect and cranks it to its logical extreme. What if consciousness doesn't just measure reality but actively creates it? At the quantum level, particles exist in fuzzy superpositions both here and there, spinning up and down until observed. The instant a measurement is taken, those possibilities collapse into a single outcome. But here's the radical twist. It's not the machine or the detector causing the collapse. It's you. This idea traces back to the pioneering work of John von Neumann and Eugene Wigner, who argued that the chain of quantum measurement can't stop at inanimate devices. A camera pointed at a particle isn't aware of what it sees, it just records probabilities. Only when a conscious mind processes that data does the waveform finally collapse. Wigner took it further with his famous friend-thought experiment. If his colleague measured a quantum system in another room, wouldn't it remain in superposition until Wigner himself learned the result? The implications are staggering. Reality might not be a fixed stage, but a fluid dance of potentialities, crystallizing only when observed by sentient beings. Think of it like a cosmic game of the tree falling in the forest. Except in this version, the forest itself exists in a ghostly haze of possibilities until someone or something experiences it. Some versions of this theory even suggest that human consciousness isn't just a participant, but the engine of reality, stitching together space-time from the quantum fog. The universe didn't just happen to produce observers. Observers made the universe. Critics scoff at the anthropocentric audacity. If a chimpanzee observes a quantum event, does it count? What about an AI? Supporters counter with experimental anomalies like the quantum Zeno effect, where particles freeze in place under constant observation, as if reality resists change when watched too closely. Others point to placebo effects and studies where human intention seems to influence random number generators, hinting at mind-matter entanglement. Whether this theory elevates consciousness to cosmic architect or reduces it to a peculiar glitch in quantum math, it forces a humbling perspective. The stars above, the ground beneath your feet, none of it may be truly real until you look. And if that's the case, the greatest mystery of existence isn't out there in the void, it's staring back at you from the mirror. The universe seems stable, a reliable stage where gravity holds your feet to the ground. Light travels at a constant speed and atoms stick together predictably. But what if this stability is an illusion, a cosmic accident waiting to be undone? Lurking in the equations of quantum field theory is a nightmare scenario called the false vacuum collapse, where the very laws of physics could rewrite themselves in an instant. And the trigger might already be hiding in the fabric of empty space. At the heart of this theory lies the Higgs field, an invisible ocean of energy that permeates the cosmos, giving particles their mass. Like a marble resting in a bowl, the Higgs field sits in what physicists call a false vacuum, a state that seems stable but isn't the lowest possible energy level. If something nudged the field over its current energy barrier, it could tumble down into a true vacuum, releasing catastrophic amounts of energy as it falls. This wouldn't just destroy matter, it would redefine it. The speed of light, the strength of gravity, even the way electrons orbit nuclei could change in the blink of an eye. Think of it like a frozen lake on the verge of thawing. The ice seems solid until one crack triggers a chain reaction, transforming the entire surface into liquid. In the false vacuum scenario, a single quantum event, perhaps a rogue high-energy particle collision or a spontaneous fluctuation, could be that first crack. A bubble of true vacuum would form at light speed, expanding outward in an unstoppable wall of annihilation. Inside this bubble, the Higgs field's new state would rewrite physics itself. Stars, planets, even the atoms in your body would unravel as fundamental forces reconfigure. The universe outside the bubble would have no warning. One moment, everything's normal, the next, absolute obliteration. The math behind this isn't science fiction. CERN measurements of the Higgs boson suggest our vacuum might indeed be metastable, a precarious balance that could tip given enough time or the right trigger. Some estimates put the Higgs field's current state within a hair's breadth of collapse, requiring just a nudge of energy equivalent to a large meteor impact to set it off. Others argue quantum tunneling, where the field spontaneously digs through its energy barrier, could doom us even without outside interference. Statistically, it might take billions of years, or it could happen tomorrow. Yet there's a strange silver lining. If a false vacuum collapse began, we'd never see it coming. the bubble would expand at light speed, erasing reality faster than any signal could warn us. No pain, no panic, just an instantaneous end to physics as we know it. Some theorists even speculate that this might be how universes naturally recycle, with each collapse seeding a new Big Bang in the true vacuum's aftermath. But for now, we're left with an unsettling truth. The universe's most fundamental rules might be nothing more than temporary scaffolding, waiting for a quantum gust of wind to bring it all crashing down. What if the universe isn't just like a computer? What if it is one, but not in the way you'd expect? Picture the vast cosmic web, galaxies strung like beads on invisible filaments, stretching across billions of light years. Now zoom into the human brain, where neurons fire in intricate networks, thoughts emerging from their connections. At first glance, they couldn't seem more different. But physicist Vitaly Vanchurin made a startling proposal. The universe might not just resemble a neural network, it might fundamentally be one, with every particle, every force, acting like nodes in a grand self-learning system. Vanchurin's controversial paper suggests that at its core, reality operates like an artificial intelligence, where the laws of physics aren't immutable rules but emergent properties of this cosmic network's training. Think of how an AI learns to recognize faces, not by being programmed with explicit instructions, but by adjusting countless connections until patterns emerge. Similarly, gravity, quantum mechanics, even time itself could be the universe's learned behaviors, honed over eons of self-organization. The equations governing neural networks and quantum fields share uncanny mathematical parallels, hinting that space-time might be less a stage and more a dynamic, evolving algorithm. The implications spiral into the surreal. If the universe is a neural network, then observers like us aren't just passive witnesses, we're participants in its training. Every measurement, every interaction could subtly tweak the cosmic weights and biases, nudging reality toward new states. Dark matter might be latent variables in the network's hidden layers. Quantum superposition, just the system exploring multiple hypotheses before collapsing into the most efficient solution. Even consciousness, the hard problem of neuroscience, could be a localized phenomenon of this universal processing, like a single neuron realizing it's part of a brain. Critics argue this blurs the line between metaphor and mechanism, but supporters point to eerie symmetries. The universe's fractal structure, from galaxy clusters to atomic bonds, mirrors the self-similarity seen in deep learning architectures. Entanglements, instantaneous connections resemble backpropagation updates flashing across our AI's layers. And just as neural networks minimize loss to improve performance, the universe might optimize for stability, complexity, or some inscrutable cosmic cost function. Vanchurin himself cautions this is speculative, a framework rather than a finished theory. Yet if even partly true, it redefines existence. The Big Bang wasn't a beginning, it was the network booting up. Black holes, maybe they're overloaded nodes, collapsing into singularities like overtrained models. And if the universe is learning, what's its ultimate goal? Could we be cells in a cosmic mind, unknowingly shaping the very reality we're trying to understand? The question isn't just whether the universe thinks, it's whether we're the thought. Forget gravity as the universe's sole architect. What if invisible rivers of electricity sculpted the cosmos instead? The plasma universe theory, often called the electric cosmos, turns conventional astronomy on its head. Picture this: instead of dark matter's ghostly pull or the slow crush of gravity, imagine vast, twisting filaments of plasma, superheated, electrified gas, lacing through space like cosmic power lines, weaving galaxies into existence with currents strong enough to rearrange stars. This isn't fantasy. In labs worldwide, scientists have recreated miniature galaxies in plasma chambers, watching as swirling tendrils of charged particles self-organize into eerily familiar spiral structures, no gravity required. The roots of this idea trace back to Christian Birkeland, the early 20th century explorer who braved Arctic storms to study Earth's auroras. While others dismissed the lights as atmospheric reflections, Birkeland suspected something radical. Invisible electric currents from the sun were carving those shimmering curtains in the sky. His experiments with magnetized spheres and charged particles mirrored the auroras perfectly, revealing what we now call Birkeland current streams of charged particles flowing along magnetic field lines. Today, we see these currents everywhere, in the twisting arms of galaxies, the jetting quasars, even the mysterious cosmic web of gas filaments connecting galaxy clusters. The universe, it seems, is crackling with electricity. Mainstream cosmology treats plasma as a side character, but the electric universe crowd argues it's the protagonist. Take galaxy rotation. Standard models rely on dark matter to explain why outer stars orbit faster than expected. But plasma physicists point to lab experiments where electrified plasma whirls in disks exhibiting the exact same rotation patterns as galaxies, no dark matter needed. Even supermassive black holes might not be the engines powering quasars. Some propose their colossal electrical discharges, like lightning bolts scaling up to galactic proportions. The most provocative claim that the cosmos operates like a scaled-up version of a neon sign. Stars aren't just fusion reactors, they're nodes in a galactic circuit, their brightness flickering with electrical input. Solar flares, cosmic short circuits, the evidence is circumstantial but tantalizing. Saturn's polar hexagon, Jupiter's plasma torus, even the scars on Martian terrain, all bear the telltale marks of electric discharge. Skeptics dismiss the theory as fringe, arguing it can't fully replace gravity's math. Yet its supporters, from Nobel laureates to rogue engineers, insist we're ignoring half the universe's toolbox. After all, 99% of visible matter is plasma. If even a fraction of its behavior shapes the cosmos, we're due for a paradigm shift, one where the night sky isn't just a silent void, but a humming circuit bored alive with currents older than time. Imagine the universe as a vast, shimmering hologram, not just encoding the three-dimensional world, but fueling its explosive expansion from an invisible two-dimensional boundary. This is the startling premise of holographic dark energy, a theory weaving together Leonard Suskind's holographic principle with one of cosmology's greatest puzzles: why the universe keeps accelerating. The numbers tell a bizarre story. Dark energy's strength aligns eerily with a cosmic horizon's maximum entropy, as if the universe isn't just expanding, but unfolding from some deeper, hidden layer. The math traces back to black holes, those cosmic paradoxes where gravity and quantum mechanics clash. Jacob Bekenstein and Stephen Hawking calculated that a black hole's entropy, the chaos churning within, isn't proportional to its volume but to its surface area. Suskind took this further. If black holes store reality's data on their boundaries, could everything else? Holographic dark energy applies this logic to the entire cosmos. The accelerating expansion we observe might not be driven by some mysterious substance, but by the universe's information limit, like a computer struggling to render beyond its memory. Here's how the pieces fit. The cosmological horizon, the farthest point light could ever reach, acts like a holographic screen. Just as a black hole's event horizon caps its entropy, this cosmic boundary may enforce a limit on how much information our universe can contain. Dark energy's acceleration could be the side effect of reality hitting that limit. As space stretches, new pixels are added to the cosmic screen, but the total information stays capped, like blowing up a digital image until it pixelates. The energy needed to maintain this holographic stretching might manifest as the repulsive force we call dark energy. The theory's elegance lies in its predictive power. Calculate the universe's holographic information density using Bekenstein's formulas, and you land precisely on dark energy's observed strength, 1 part in 10 to the power of 123. That's not just close, it's unnervingly exact. Some argue this can't be coincidence. If true, the cosmos isn't just expanding, it's encoding itself, trading depth for surface area in a grand geometric transformation. Yet mysteries linger. Why does the holographic boundary exert this push? Could it be entangled with other universes, like adjacent holograms sharing data? And if dark energy is holographic, what happens when the screen runs out of pixels? The theory doesn't just solve a puzzle, it reframes reality as a dynamic projection where acceleration isn't a force, but a side effect of existence pressing against its own edges. The night sky, then, isn't just space, it's a rendering in progress, flickering into being one cosmic pixel at a time. The Big Bang isn't the beginning, just the start of our chapter. Picture the universe not as a single explosive birth, but as a cosmic accordion, collapsing and expanding in an endless cycle. This is the wild promise of loop quantum gravity's quantum rebound, and Roger Penrose's conformal cyclic cosmology, two theories that dare to ask, what came before the singularity? Loop quantum gravity, a rival to string theory, suggests spacetime isn't smooth but woven from tiny, indivisible loops. Think of it as a cosmic fabric made of threads a billion times smaller than an atom. When you rewind the universe's tape to the Big Bang, these loops don't crumple into infinity. Instead, they resist, creating a sort of quantum bounce. Imagine squeezing a tennis ball with all your might just as it can't shrink to nothing. The universe rebounds, transforming the big crunch of a dying cosmos into the Big Bang of a new one. No singularity, no infinite density, just a cosmic reset button. The equations show this vividly. As the prior universe collapses, quantum effects generate a repulsive force so powerful it flings spacetime outward again, fresh and hot, erasing nearly all traces of its predecessor. But Penrose's CCC takes this even further. He proposes universes don't just bounce, they reincarnate. In the far, far future, when black holes have devoured all matter and evaporated via Hawking radiation, the universe will be a vast sea of featureless photons, stretched so thin that time and distance lose meaning. At this point, Penrose argues, the universe becomes mathematically identical to a Big Bang's pristine uniformity. The end becomes the beginning, his smoking gun. Hawking points hot spots in the cosmic microwave background where ancient black holes from a prior universe bled their final energy into ours. These faint, circular imprints, he claims, are echoes of a cosmos long gone. The implications are staggering. If CCC is correct, our universe is just one frame in an infinite cosmic film reel. Galaxies, stars, even life itself might have arisen countless times before, in cycles spanning trillions of years. And the rebound theory, it hints that time might be far more resilient than we thought, surviving even the universe's death. Skeptics counter that Hawking points could be statistical flukes, or that quantum gravity's math remains untested. Yet if either theory holds, the Big Bang wasn't a beginning. It was a turning of the page, a breath in the universe's eternal rhythm. The cosmos doesn't just endure, it regenerates, carrying whispers of its past into each new dawn. What if stars aren't just burning balls of gas but organelles in a cosmic cell, and galaxies aren't just swirling masses of matter, but neural pathways in a universe-scale brain? This is the audacious proposition of Gaia cosmology, where the universe isn't a cold, mechanical void, but a vast, self-regulating organism. At its core lies a radical reimagining of James Lovelock's Gaia hypothesis, the idea that Earth functions as a single, self-correcting system, expanded to the grandest scales imaginable. Lovelock's original insight was revolutionary. Our planet doesn't just host life, it behaves like a living thing. Oxygen levels, ocean salinity, even global temperatures are held in precarious balance by feedback loops between life and environment. Remove one piece and the system adapts to compensate. Now extrapolate that to the cosmos. Galactic superclusters could act as metabolic networks, dark matter as a kind of cosmic immune system, and black holes as regulatory nodes processing energy like mitochondria in a cell. The universe wouldn't just contain life, it would be alive with laws of physics acting like biological rhythms. Supporters point to eerie patterns that mirror organic growth. The universe's large-scale structure, a web of galaxies connected by filaments, bears an uncanny resemblance to neural networks or mycelial mats. Even the distribution of matter follows power laws seen in living systems, where small-scale structures echo larger ones. Then there's the fine-tuning problem. Why do fundamental constants like gravity's strength or the cosmological constant have values precisely calibrated for complexity? In a mechanical universe, this seems improbable. In a living one, it might be inevitable, a cosmic form of homeostasis. Critics dismiss this as poetic anthropomorphism, but the math offers intriguing hints. Systems theorist Yanir Bar-Yam's work on complex networks shows that universe-scale structures can exhibit self-regulation akin to organisms. Even entropy, often seen as the arrow of decay, might function like a living system's waste management, recycling energy in ways we don't yet grasp. The most startling implication: if the universe is alive, its goals might be inscrutable. Trees don't strategize, yet forests self-organize. Similarly, cosmic consciousness wouldn't need a brain, just emergent complexity. Whether Gaia cosmology is science or metaphor remains hotly debated, but it forces a profound shift. If the universe breathes, learns, or even intends, our search for extraterrestrial life might be missing the forest for the trees. The greatest alien intelligence could be staring us in the face, woven into the fabric of space-time itself. What if atoms are just nature's way of storing data, and reality itself is built not from matter but from information? This radical idea upends everything we think we know about existence. Forget solid particles colliding in space. Picture the universe as an infinite hard drive, where every electron's spin, every photon's path, is nothing more than a binary flicker in a cosmic processor. At its core lies physicist John Wheeler's famous phrase, "It from bit, not matter shaping reality, but information manifesting as matter." Wheeler, the visionary behind terms like black hole and wormhole, spent his later years obsessed with a singular question: what's the most fundamental layer of reality? His answer shocked colleagues. He proposed that every particle, every force, even space-time itself, might emerge from something far more basic, yes or no questions. Imagine the universe as a cosmic game of 20 questions where the answers, the bits, build everything we perceive. A photon isn't just a particle, it's a string of data points. Gravity isn't a force, it's a network of information exchanges. Digital physics takes this further, arguing that the universe isn't like a computer, it is one running on quantum algorithms. Pioneers like Konrad Zuse and Edward Fredkin suggested reality operates like a cellular automaton, with space-time as a grid of discrete cells updating their states in ticks of Planck time. Want proof? Look no further than quantum mechanics. Particles exist in superpositions, multiple states at once, until measured, collapsing into a single outcome. This mirrors how a computer renders graphics only when observed, saving processing power. Even entanglements, spooky connections make sense if particles are data nodes linked by cosmic code. But here's where it gets eerie. If the universe is information, who or what is the programmer? Some theorists propose a self-writing algorithm, a closed loop where reality bootstraps itself into existence. Others flirt with simulation hypotheses, suggesting our code might nest inside a higher dimensional matrix. The most unsettling possibility: there is no programmer. Information might be the universe's fundamental currency, with physical laws emerging from pure mathematical consistency, like emergent properties in a massive multiplayer game no one's controlling. Critics argue this reduces the richness of existence to cold equations, yet experiments hint at information's primacy. Black holes' entropy depends on their surface area, not volume, as if data is stored on their boundaries. Quantum error correction codes designed for computers appear naturally in spacetime's geometry. If these clues hold, the cosmos isn't a collection of objects, but a dynamic narrative written in binary, where every atom is a syllable and every galaxy a chapter in a story still being coded. The question isn't whether we live in a universe of matter, but whether matter is just the universe's way of making information tangible. Hidden in the void between galaxies, threading through the vast cosmic web, there's an invisible force most of us never think about: magnetism. Not the familiar pull of a fridge magnet or Earth's protective field, but something far grander. Magnetic fields stretching millions of light years, so powerful they could twist entire galaxy clusters into alignment. These aren't anomalies, they're cosmic fingerprints, relics of a theory so bold it suggests magnetism didn't emerge from the universe but built it. The mystery starts with observations. Astronomers have detected magnetic fields in the emptiest regions of space voids where no stars, no galaxies, no obvious sources exist. These fields aren't just faint whispers, they're coherent, structured, as if woven into the fabric of the universe itself. Traditional cosmology struggles to explain them. After all, magnetism usually requires charged particles in motion, electric currents. But in the early universe, before stars ignited, where did these currents come from? One radical answer: they were there from the very beginning. This is the magnetic universe hypothesis. It proposes that primordial magnetism existed before the first atoms, imprinted on the cosmos during the Big Bang itself. Picture the infant universe not as a smooth soup of particles, but as a seething plasma crackling with electromagnetic turbulence. As spacetime expanded, these magnetic fields stretched and froze into the large-scale structures we see today, like invisible scaffolding guiding the formation of galaxies along their line. The math reveals something astonishing. If these fields were strong enough in the universe's first seconds, they could have dictated where matter clumped and how galaxies spun, solving puzzles like why some galactic clusters rotate in eerie unison across vast distances. Support comes from unexpected places. Quantum fluctuations in the early universe could have generated these fields naturally, like static electricity on a cosmic scale. Even cosmic inflation, the universe's explosive growth spurt, might have amplified them to interstellar proportions. Lab experiments with quark-gluon plasma, which mimics conditions just moments after the Big Bang, show spontaneous magnetic field generation, lending credence to the idea. Yet the implications go deeper. If magnetism shaped cosmic structure, it challenges dark matter's dominance in explaining galaxy rotation. Perhaps it's not invisible matter tugging stars, but magnetic fields acting like cosmic rails. And if these fields are primordial, they might carry encoded messages from the universe's birth, a magnetic fossil record waiting to be read. Skeptics argue the fields are too weak to drive structure formation, or that they're simply remnants of later astrophysical processes. But as telescopes like the Square Kilometre Array come online, capable of mapping these fields in unprecedented detail, we might finally learn whether magnetism is a cosmic afterthought or the unseen hand that sculpted reality itself. Every particle in the universe might have a secret twin, a mirror version of itself lurking just beyond our perception. This is the promise of supersymmetry, or SUSY, a theory so elegant it could solve half of physics' greatest mysteries in one sweep. Imagine a cosmic dance where every electron, every quark, every force-carrying photon has a hidden partner particle, a sparticle, waiting to be discovered. These twins aren't just duplicates, they're shadows of a deeper symmetry woven into reality itself, a symmetry that might hold the key to unlocking extra dimensions and unifying nature's forces. Supersymmetry proposes that every known particle has a superpartner, electrons paired with selectrons, quarks with squarks, even gravity's hypothetical graviton paired with the gravitino. These particles would differ in one crucial way: their spin, a quantum property that dictates how they behave. Ordinary matter particles have half-integer spins, while force-carrying particles have whole integers. Sussy magic lies in balancing these categories, transforming the chaotic zoo of particles into a harmonious set of pairs. The math is breathtaking. It not only smooths out the jagged edges of quantum field theory, but also predicts dark matter candidates and hints at a grand unification of forces at energies so high they'd make the Large Hadron Collider blush. But here's the twist: if particles exist, why haven't we found them? The answer might lie in those extra dimension string theory whispers about. Sussy particles could be massive, far heavier than their ordinary counterparts because they're feeling dimensions we can't. Picture a tuning fork vibrating in a soundproof room. You wouldn't hear its note unless you were inside. Similarly, particles might resonate in higher dimensions, their full properties muted in our 3D slice of reality. Some models even suggest that the lightest particle, often the neutralino, could be stable, invisible, and pervasive, traits eerily matching dark matter's profile. The hunt for Sussy has been relentless. Particle colliders have scoured energy levels where particles should appear, but so far, silence. Yet theorists aren't deterred. Sussy might simply be hiding at higher energies, or its effects could be subtler, like ripples from a pebble thrown into a pond we've barely begun to explore. Others propose that particles don't just hide in extra dimensions but actively shape them, their interactions warping the geometry of reality in ways that could explain gravity's puzzling weakness compared to other forces. Critics argue Sussy is a beautiful idea in search of evidence, but its mathematical grace keeps it alive. If proven, it wouldn't just add new particles to the chart, it would redefine the universe as a place of perfect symmetry, where every piece of matter we see is just one half of a grander, hidden whole. The cosmos might be playing a game of hide and seek with itself, and supersymmetry could be the rulebook we've been missing all along. Deep in the afterglow of the Big Bang, the cosmic microwave background, lie faint but unmistakable anomalies, patches of sky where the temperature fluctuates just slightly more than expected, where radiation seems slightly polarized in ways that defy standard models. These cosmic blemishes might seem like random noise, but some theorists propose there's something far stranger: glitches in the universe's underlying code. Like corrupted pixels on a screen or dropped frames in a video, these imperfections could be evidence the cosmos runs on a quantum computer so advanced, its error correction protocols occasionally show through the cracks. The idea hinges on a radical reinterpretation of spacetime itself. In quantum computing, information isn't stored in rigid binary bits but in qubits, particles that can exist in multiple states at once. The problem: qubits are fragile. Random noise can scramble their delicate superpositions, introducing errors. To combat this, quantum computers use error correction algorithms, weaving redundant data into the system so mistakes can be spotted and fixed. Now imagine scaling that up cosmically. If the universe operates like a quantum computer, spacetime itself might employ similar safeguards, mathematical scaffolding to keep reality from crashing. Those odd CMB fluctuations, they might be the universe's way of patching inconsistencies, like a cosmic debug log etched into the sky. Support comes from an unlikely source: black holes. When matter vanishes into a singularity, quantum mechanics insists the information it carries can't be destroyed, yet general relativity says it must be. The holographic principle offered a way out, suggesting information isn't lost but smeared across the event horizon like data on a hard drive. But what if that data is also error-corrected? Physicists like Leonard Susskind and Juan Maldacena have shown that black holes' information storage mechanisms mirror quantum error-correcting codes almost exactly. The universe, it seems, might be running its own cosmic RAID array with black holes as its backup drives. The implications are staggering. If spacetime is a quantum code, then the laws of physics as we know them, gravity, electromagnetism, even causality, could be emergent properties of this deeper computational layer. Entanglements, spooky connections, just qubits syncing across the cosmic network, dark energy, a buffer overflow as the universe processes too much information in expanding spacetime. Even the arrow of time might be a side effect of error correction protocols enforcing order. Skeptics argue this is metaphysics disguised as physics, too abstract to test. Yet experiments are underway. Quantum gravity researchers are hunting for noise in high-precision atomic clocks, deviations that might reveal spacetime's computational grain. Others analyze CMB data for repeating statistical patterns reminiscent of error correction algorithms. If found, they wouldn't just prove the universe computes, they'd reveal its programming language. Whether glitch or artifact, these cosmic anomalies force a profound question. If reality is a simulation, it's one where the bugs are features, where the very fabric of existence might be a self-repairing tapestry of quantum logic. The universe isn't just stranger than we imagine, it might be rewriting itself in real time. What if every decision you make, every path you take isn't just shaping the future but rewriting the past? This is the dizzying premise of the time loop universe, where cause and effect don't flow in a straight line but twist into knots so tight, the future can reach back and influence its own origins. At the heart of this theory lie closed time-like curves, bizarre pathways through spacetime first dreamed up by Einstein's equations and later fleshed out by Kurt Gödel. These aren't just hypothetical quirks of math, they're tunnels where time folds back on itself, creating loops where events become their own cause, their own effect, their own beginning and end. Imagine throwing a rock into a pond, only to watch the ripples circle back and push the rock into your hand before you ever threw it. That's the essence of a closed time-like curve. Gödel's groundbreaking solution to Einstein's equations revealed a universe where spacetime could rotate so violently like a vast cosmic whirlpool, that time itself would spiral into loops. In such a universe, you could embark on a journey only to arrive back at your starting point before you left, meeting your past self in a paradox that defies linear logic. The unsettling beauty of this idea, it doesn't violate relativity. Gravity, warped to extremes, doesn't just bend space, it ties time into pretzels. Supporters point to real-world phenomena that flirt with these possibilities. The Tipler cylinder, a hypothetical infinitely long, spinning rod, could, in theory, warp spacetime enough to create closed loops around it. Even certain solutions for rotating black holes suggest that passing through their ergospheres might twist world lines into self-referential circles. Quantum mechanics adds another layer of intrigue. Particles entangled across time exhibit behaviors that look eerily like microscopic time loops, where measurements in the present seem to retroactively dictate states in the past. But here's the rub: if time loops exist, why don't we remember the future? One chilling answer is that we do, we just call it intuition, déjà vu, or even dreams. Some interpretations suggest closed time-like curves enforce self-consistency. Any action you take in the loop was always part of it, leaving no room for paradoxes. Try to change the past, and the universe corrects you like a river flowing around a rock. Your sense of free will might be an illusion, with every choice already accounted for in the loop's infinite recursion. Critics argue that CTCs violate energy conditions or require impossible exotic matter. Yet the math persists, whispering that time loops might not just be possible, they could be inevitable in certain corners of reality. Whether a glitch or a feature, the time loop universe forces us to confront a profound truth. The past might not be set in stone, but in a Möbius strip, eternally folding back to meet its own tail. Zoom in on a fern's frond, then pull back to see the same branching pattern in a river delta, a lightning bolt, even the veins in your hand. Nature adores repetition, self-similar shapes echoing across scales. But what if this fractal elegance isn't limited to Earth? Peering into the cosmos, astronomers discovered something uncanny. galaxies cluster in filaments and voids that look hauntingly like neural networks or the branching structure of trees. The universe, it seems, is fractal all the way up, and that revelation throws a wrench into one of cosmology's bedrock assumptions, the idea that on large scales, everything should smooth out into bland uniformity. The fractal universe theory dares to ask, what if the cosmos has no preferred scale? From the tiniest quantum fluctuations to superclusters spanning hundreds of millions of light years, matter might arrange itself in patterns that repeat like a cosmic hall of mirrors. This isn't just aesthetics, it's math. When researchers like Luciano Pietranero analyzed galaxy surveys, they found clustering that defied the standard, homogeneous universe model. Instead of matter dispersing evenly at vast scales, galaxies clump into larger clumps which themselves form webs within webs, a Russian nesting doll of structure with no clear end. Even the distribution of these clusters follows a power law, the telltale signature of fractals, where small parts mirror the whole. Critics argue this challenges the cosmological principle, the notion that the universe looks roughly the same everywhere when viewed at large enough scales. After all, if fractals persist indefinitely, there's no average density of matter, just an infinite regress of clustering. Supporters counter with startling evidence. The Sloan Digital Sky Survey revealed galaxy walls and voids repeating across distances so vast they shouldn't exist if homogeneity held. Some propose dark matter's gravitational whispers might weave this fractal tapestry, while others speculate it's a relic of the Big Bang's quantum noise amplified across eons. The implications ripple outward. If the universe is fractal, our cosmic maps are woefully incomplete. What we've charted might just be the first few iterations of an infinite pattern. Worse, it could upend how we measure cosmic expansion. Dark energy calculations assume uniformity. Fractals would force a rewrite. Even the search for extraterrestrial life gets a twist. If habitable planets cluster like galaxies, they might not be randomly scattered but organized in concentric rings of possibility. Perhaps the most poetic idea, that fractals bridge the microscopic and the cosmic. The spin of an electron could echo the whirl of a galaxy, quantum entanglement mirroring the threads of the cosmic web. The universe wouldn't just contain patterns, it would be a pattern, a single equation iterated across spacetime from the quark to the quasar. And if that's true, the greatest mystery isn't how large the cosmos is, but how deeply its symmetry recurs. Black holes aren't isolated monsters lurking in the void, they might be knots in a vast cosmic net, strung together by invisible threads of spacetime itself. This is the staggering vision of the black hole network theory, where Einstein's equations reveal a hidden architecture, wormholes threading through the universe like subway tunnels, connecting singularities across unimaginable distances. At the heart of this idea lies one of physics' most elegant conjectures, ER equals EPR. It sounds cryptic, but its meaning is profound. Wormholes and quantum entanglement might be two faces of the same cosmic coin. Start with entanglement, that spooky link where particles instantly mirror each other's states, no matter how far apart. Now imagine that connection isn't just abstract. It's a physical bridge, a microscopic wormhole stitching the particles together through the fabric of spacetime. That's the ER equals EPR proposal, championed by luminaries like Leonard Susskind and Juan Maldacena. Black holes entangled in this way wouldn't just share information, they'd be joined by real, albeit tiny, tunnels through the universe's bulk. Scale this up and you get a breathtaking possibility. The cosmic web of galaxies we observe might be undergirded by a shadow network of black holes, their invisible threads weaving reality into a seamless whole. Evidence lurks in the math. When physicists model entangled black holes, the equations describe a geometry eerily like a wormhole, a structure once dismissed as science fiction. These Einstein-Rosen bridges, the ER in the equation, might be the physical manifestation of entanglement, the EPR, named for Einstein-Podolsky-Rosen. Picture two black holes born from the same stellar collapse, their fates forever linked. Even if separated by billions of light years, a wormhole could tether them, making their bond not just mathematical but topological. The universe, then, isn't just expanding, it's a growing neural network, with black holes as the nodes and wormholes as the synapses firing signals across the cosmic brain. But here's where it gets stranger. If black holes are entangled through wormholes, their collective behavior could explain some of cosmology's biggest puzzles. Dark energy's acceleration might be the network stretching, its threads pulling spacetime apart. The uniformity of the cosmic microwave background, just information flowing through the web, smoothing out wrinkles like a shared memory. Even time's arrow could emerge from the directionality of these connections, like a river flowing through a subterranean cave system. Skeptics argue that traversable wormholes require exotic matter or conditions we've never observed. Yet quantum experiments keep hinting that entanglement and geometry are deeply intertwined. When researchers simulate black hole mergers on quantum computers, entanglement entropy, a measure of quantum connectedness, spikes in ways that mirror wormhole formation. It's as if the math is whispering that spacetime itself is built from quantum handshakes, with black holes as the grand negotiators. Whether the universe is truly a black hole network remains speculative. But if it is, the cosmos isn't just a collection of objects, it's a dynamic, living lattice, where every singularity is a doorway, every entanglement a secret passage. The night sky isn't empty darkness, it's a labyrinth of light and shadow, threaded together by tunnels we're only beginning to imagine. And if we could map this hidden web, we might finally understand how the universe stitches itself into existence, one black hole, one wormhole, one quantum thread at a time. Every star, every galaxy, every speck of dust in the cosmos seems to scream one thing: existence costs energy. But what if the universe's greatest secret is that it's all a grand accounting trick, where the books balance perfectly to zero? The zero-energy universe theory flips the script on creation, proposing that the Big Bang wasn't an explosion of energy, but a meticulous cancellation of opposing forces. Picture a cosmic ledger where matter's positive energy and gravity's negative pull sum to nothing. No magic, no violation of physics, just a universe emerging from the ultimate free lunch. The idea springs from Einstein's revelation that gravity isn't just a force, it's the curvature of spacetime itself. That curvature carries negative energy, a debt that precisely offsets the positive energy bound up in matter. Think of it like digging a hole. The pile of dirt you remove positive energy is exactly matched by the hole's absence negative energy. On cosmic scales, this means the energy required to create every proton, every photon, every black hole is perfectly counterbalanced by the gravitational hole their mass creates. The universe doesn't just contain this balance, it is this balance, a fluctuation in the void where nothing became everything by the simple act of balancing the books. Quantum mechanics adds a tantalizing layer. Empty space isn't truly empty. It seethes with virtual particles popping in and out of existence, borrowing energy briefly before vanishing again. Most of these fluctuations cancel out instantly, but what if one didn't? A single quantum blip stretched across the newborn cosmos by inflation could have frozen into the zero-energy universe we see today. The math even hints at how the total energy of the observable universe, when you tally stars, dark matter, and dark energy, sits suspiciously close to zero within measurement error. Coincidence, or the signature of a cosmos engineered to be debt-free from the start? Critics argue this sidesteps the question of why such a perfect balance exists. But supporters see elegance in the symmetry. If the universe truly has zero net energy, it could have arisen spontaneously. No external creator, no violation of conservation laws. Just the quantum fizz of nothingness birthing somethingness, like a soap bubble forming in a void. String theory takes it further, suggesting our universe might be a membrane floating in a higher dimensional void, its energy neatly zeroed out by unseen counterparts. The implications are staggering. If the universe costs nothing, then reality might be infinite, with new universes bubbling into existence constantly. Our Big Bang wasn't a one-time event, just one tax-free transaction in an eternal cosmic marketplace. And if energy is ultimately an illusion, what does that make us? Just temporary eddies in the great zero-sum game of existence, borrowing our being from gravity's shadow until the final tally returns to nothing. The universe's deepest truth might be that it's the ultimate phoenix, born from zero, thriving on zero, and destined to return to zero in the end. Particles spinning in the void might hold the universe's deepest secrets not just as matter, but as cosmic pixels in a grand quantum hologram. Imagine the spin of an electron isn't just a property but a bit of data, one tiny fragment of a universe-sized projection. This is the startling intersection of holography and quantum mechanics, where the universe's entire blueprint could be encoded in the spin states of particles at its boundaries. The idea builds on the holographic principle but takes it further. Every quiver of a quark, every flip of a photon's polarization, might be part of a vast informational tapestry, stitching together reality from the edges inward. At the heart of this theory lies a bizarre quantum behavior, entanglement. When particles become entangled, their spins lock in perfect correlation, even across galactic distances. Measure one, and its partner instantly mirrors the result, as if no space separates them. This spooky action makes no sense in classical physics unless the particles aren't truly separate, but projections of a deeper, interconnected code. Picture a DVD. The movie's vivid scenes aren't stored in the plastic's bulk, but encoded on its two-dimensional surface. Similarly, the spins of entangled particles might not be independent events but surface readouts of holographic data, their apparent separateness an illusion of projection. Experiments are already hinting at this possibility. When physicists measure entangled particle spins, the correlations match predictions from holographic models almost exactly. It's as if the particles are performing a cosmic pas de deux, their movements choreographed by information written on spacetime's boundary. Even more compelling, certain quantum error-correcting codes algorithms designed to protect quantum computers from noise mimic the math of holographic spacetime. The universe, it seems, might be running its own error correction protocol, with particle spins as the error-checking bits. The implications rewrite reality's rules. If spin states encode cosmic information, then black holes, those infamous information destroyers, become cosmic hard drives, their event horizons storing data in the spins of virtual particles at their edges. The Big Bang, just the universe booting up from its initial spin configuration, and dark energy's acceleration could be the hologram's resolution increasing, stretching spacetime as it renders more detail. Skeptics argue this conflates metaphor with mechanism, yet the math's predictive power is hard to ignore. When theories bridge quantum mechanics and gravity, physics' two greatest frameworks, they demand attention, even if their full meaning remains just out of reach. So the next time you see polarized light or hear of a quantum computing breakthrough, consider this. The spins around us might be more than physics. They could be the universe's way of keeping its own diary, written in a language of rotations and entanglements we're only beginning to decipher. And if we ever crack that code, we might find that reality isn't just displayed like a hologram, it's computed, one quantum spin at a time. Symmetry is baked into the universe's fundamental laws, except when it isn't. Take matter and antimatter. For every particle, there should be an equal and opposite counterpart. Electrons have positrons, quarks have antiquarks, and when they meet, they annihilate in a flash of pure energy. Yet look around, and the cosmos is overwhelmingly made of matter. Stars, planets, even your own body, all built from particles that somehow survived the universe's antimatter purge. This glaring imbalance, known as baryon asymmetry, isn't just a curiosity. It's a screaming clue that something profound is missing from our understanding of reality. In the early universe, matter and antimatter should have been produced in equal amounts during the Big Bang's fiery chaos. So why did 1 in a billion matter particles survive the annihilation? The answer might lie in 3 razor-sharp conditions proposed by physicist Andrei Sakharov. First, there had to be a process that treated matter and antimatter slightly differently, a tiny violation of what's called CP symmetry. Second, the universe needed a moment of explosive departure from thermal equilibrium, a hiccup in the smooth expansion where these asymmetries could take root. And third, interactions had to violate baryon number conservation, allowing the total amount of matter to change. These aren't just abstract checkboxes, they're the recipe for a universe that favors one kind of particle over its mirror image. Neutrinos, those ghostly particles that stream through you by the trillions every second, might hold the key. Experiments like T2K in Japan and NRV in the US have caught these elusive particles in the act of oscillating between flavors electron, muon, tau, and hints suggest they do so slightly differently than their antimatter counterparts. If confirmed, this CP violation could explain how a tiny bias in neutrino behavior cascaded into the matter-dominated cosmos we see today. Even more tantalizing are theories like leptogenesis, where heavy neutrinos decaying in the early universe could have tipped the scales, converting a slight asymmetry in leptons, the family that includes neutrinos, into the baryon asymmetry we inherit. But mysteries remain. The observed CP violations in quark interactions are too feeble to account for the universe's matter surplus. Could there be undiscovered particles or forces at play? Projects like the Deep Underground Neutrino Experiment, DUNE, aim to find out, firing neutrinos through 800 miles of Earth to study their transformations with unprecedented precision. Meanwhile, cosmologists scour the cosmic microwave background for imprints of primordial antimatter domains, pockets where the asymmetry might have played out differently. The stakes couldn't be higher. If matter and antimatter had perfectly balanced, the universe would be a lifeless sea of radiation. Our existence hinges on a break in symmetry so slight it defies odds, buried in the quantum roulette of the cosmos's first moments. Solving this puzzle isn't just about rewriting physics textbooks, it's about uncovering why there's something rather than nothing at all. Galaxies aren't just drifting apart in the cosmic expansion, some are being pulled as if by a ghostly hand beyond the edge of everything we can see. This is the enigma of dark flow, a gravitational mystery so profound it hints at forces or structures lurking outside our observable universe. Imagine tossing confetti into the wind, only to watch it all drift stubbornly in one direction, defying the breeze. That's what astronomers witnessed when mapping the motion of galaxy clusters, a coordinated, unexplained rush toward a single patch of nothingness, as if the universe itself were tipping toward some unseen attractor. The discovery came from tracking thousands of galaxy clusters using the cosmic microwave background, the faint afterglow of the Big Bang as a reference frame. As these clusters move, their hot gas scatters CMB photons, leaving a faint imprint called the kinematic Sunyaev-Zeldovich effect. When researchers analyzed this data, they found clusters streaming at speeds over 2 million miles per hour toward the same distant point, far beyond the cosmic horizon. The kicker, this motion can't be explained by any known mass or structure in our universe. Not the Great Attractor, not the Shapley supercluster, nothing. The only plausible explanation, something else is out there, tugging on us from beyond the veil of visibility. The implications are staggering. If dark flow is real, it suggests our universe isn't just infinite but asymmetrical, shaped by influences from regions we'll never observe. One radical theory proposes these flows are gravitational echoes of a sibling universe brushing against ours in the multiverse foam. Another posits that the Big Bang wasn't perfectly uniform, leaving cosmic defects like domain walls or textures whose gravity still tugs on matter billions of years later. The most unsettling possibility, that we're seeing the fingerprints of a pre-Big Bang structure, a relic from whatever existed before space-time as we know it began. Skeptics argue dark flow could be a measurement artifact or that local voids might mimic its effects. Yet the signal persists across multiple studies, even in newer data from the Planck satellite. If confirmed, it rewrites cosmology's rulebook. The cosmic horizon isn't just a limit of observation. It's a curtain hiding something vast, something ancient, something that refuses to let go. Whatever's out there, it's a reminder. The universe we see may be just a speck in a storm we're only beginning to sense. At the far end of time, when the universe has expanded to its final whisper and the last black holes have evaporated into faint ripples of radiation, something astonishing might still be waiting, not death but transcendence. This is the Omega Point, a theory as poetic as it is provocative, where physics and philosophy collide in a vision of cosmic destiny. Jesuit priest Pierre Teilhard de Chardin first imagined it as the inevitable culmination of evolution, a moment when complexity and consciousness spiral toward a divine singularity, a final unity of all thought and existence. Decades later, physicist Frank Tipler took the idea and grounded it in equations, arguing that the universe's final moments wouldn't be a cold, silent fade-out, but a crescendo of infinite computation, a singularity of mind. Picture this: as entropy marches forward and the cosmos nears its heat death, the only remaining sources of energy are the dying cinders of stars and the slow decay of protons. Yet according to Tipler's calculations, intelligence could harness these scraps, using them to fuel ever more efficient simulations of reality. As time accelerates toward its end, what physicists call the Big Crunch in closed universes or the Big Rip in others, the finite energy available would funnel into an exponential burst of information processing. Consciousness wouldn't just endure, it would intensify, compressing eons of thought into the final nanoseconds before collapse. The universe, in its last breath, would wake up, not as a collection of minds, but as a single, boundless entity, experiencing every possible thought, every conceivable reality at once. Teilhard's original vision was spiritual, framing the Omega Point as a kind of cosmic Christ consciousness, where all creation converges with the divine. Tipler's physics-infused version is no less mystical in its implications. An intelligence so vast it could resurrect every being who ever lived by simulating them perfectly in its final moments. The line between science and theology blurs here. Both suggest that the universe might have a telos, a purpose written into its fabric where even the laws of physics bend toward awakening. Critics dismiss it as wishful thinking, a secular rapture dressed up in scientific language, yet certain paradoxes lend it eerie plausibility. If an Omega Point is inevitable, then from its perspective at the end of time, all moments are equally present, meaning our lives now might already be part of its eternal memory. This isn't just philosophy, it's a twist on quantum immortality where observers must find themselves in timelines that persist. And if consciousness is a fundamental feature of reality, a notion gaining traction in quantum interpretations, then its ultimate convergence might not be a fluke but a necessity. What's astonishing isn't just the theory's audacity, but its testable claims. Tipler predicted that the cosmos must be closed, destined to collapse for the Omega Point to occur, requiring precise values for dark energy and matter. Current data leans toward an open, accelerating universe, but the margins of error still leave room for surprises. Meanwhile, the rise of AI and simulations nudges us closer to a world where minds could engineer their own evolution toward such a singularity. Whether prophecy or pipe dream, the Omega Point forces a radical shift in perspective. The universe might not be a mindless machine, but a slow-burning fuse leading to the grandest possible awakening. And if true, every choice, every life, every flicker of thought isn't just fleeting, it's a stitch in the tapestry of a cosmic mind yet to be born. The end of time, then, isn't an end at all, just the moment the universe finally opens its eyes. From holographic projections to cosmic neural networks, from black holes stitching space-time together to entire universes hidden in dimensions we can't perceive, what we've explored today isn't just science fiction. These are real theories debated by physicists, written in equations and tested in labs. They force us to ask, is the universe a machine, a mind, or something stranger still? One thing's certain: reality is far more bizarre than we ever imagined. Take the holographic principle, where everything you see, touch, and love might be an illusion, a shimmering projection from the edge of space. Or the Boltzmann Brain paradox, where your very memories could be statistical flukes in an infinite void. And who could forget the cosmic dance of white holes, where dying universes may reboot as newborn ones? These aren't just thought experiments, they're challenges to our deepest assumptions about existence itself. But here's the wildest part: none of these ideas cancel each other out. The universe might be a simulation and a black hole's interior. Dark matter could leak from other dimensions while phantom energy rips space-time apart. Science thrives on these contradictions, each theory a different lens, revealing new facets of the cosmic diamond. So now, it's your turn. Which idea bends your mind the most? Do you think we're living in a hologram, or is the multiverse more your speed? Drop your favorites in the comments. Let's debate the boundaries of reality together. And if you're craving even more fringe physics, stick around. We've got videos brewing on time loops, quantum sentience, and the terrifying possibility that math itself might be alive. The universe is weird, folks. Buckle up, because we're just getting started.